The speed of an object. Given what? Or, because what are you thinking? Given what?
Well, I'm just going based off of the homework.
Is there a certain number? Let's just look at it. What number? 2 and 3? 2 says, this is from homework number 3, chapter 3, number 2. Calculate the instantaneous speed in meters per second at the, and the value changes. So the one I have at the moment was 12-second mark for a car that accelerates at 4 meters per second squared from a position at rest. So this is what I like to do. I like to write down the things I know, especially if you don't know where to go from there. So if it's an initial position, so I use the little circle. It represents naught. That'd be x naught. It's the initial position. You can use an I or anything you want to, as long as you know it's initial position. It's starting at 0. It's going to end up somewhere else. It didn't tell us that, right? It tells us the acceleration, which in this case, 4 meters per second squared. Time, it gives us time, the 12-second mark. So 12 seconds later, it wants to know that velocity. All right. So I think you got the picture. It's a car that accelerates and gets up to a certain speed. Well, how fast will it be going? Conceptually, what's going to be happening? Speeding up at a certain rate. Very good. Every second, let's rewrite this one. Every second, its velocity will change by 4 meters per second. So if we do that for 12 seconds, what will it get up to? 4 times 12, 48. Jesus. Oh, it matches. So conceptually, it's just, does that make sense? Equation-wise, our guide to thinking, acceleration was a change in velocity with time. So I'm going to rewrite that as the change in velocity is acceleration times that change in time. We've seen these before. And can you tell that this is the acceleration, 4, and the time is 12. So yeah, you get 48. Do you see how the units cancel out as well? You can say you're never sure what the units should come out as. There's 2 ways I like to look at it. One, they cancel too. Let's just take those, because some people get confused with this in this class. Meters per second. And we're going to multiply that by seconds, which if you remember, you can write as a fraction as over 1. It's the same thing. Do you see how the seconds will cancel? And what are you left with? Meters per second. Good, because this is velocity. It should be velocity. And that's the second way. You can just go, well, what's the units for velocity? Miles per hour. Well, wait, I was using SI units, standard units, meters and seconds, so it should come out meters per second. It's another way to gauge yourself if you ever get confused with units. So, yeah, it's here. This equation guides our thinking. It's the relationships between them. And you can either just plug it in and you get the answer, or understand what it means conceptually like we just discussed here, and that'll help you out. Right, Mark? Good. Was there a second one? Number 3. It says calculate the speed of a skateboarder who accelerates from rest, same thing, for 2 seconds, same thing, down a ramp with a certain acceleration. So actually it's exactly the same. It gives you all the same stuff. Let's say you didn't start from rest. You were going already 10 meters per second. Could you do it then? If your initial velocity was 10 meters per second? How fast would this be going after 12 seconds if it started going 10 meters per second? Yeah, 10 more, because it was already going 10. You just tack it on. It changed. The change in velocity is that. Since it started from 0, you're now at that. But if you started at 10, if it helps, remember your change in velocity is the final velocity minus the initial velocity. So if you start at 10, this will have to be that 58 to make the difference 48. Other questions? All right. Clickers, we're going to try. Since I meant to last time. Okay, so the way this works, in the bottom right-hand corner, you see the channel. That's for actual clicker. Something like this. So make sure you're on channel 41. It's the default. The only reason to make it different is if some other adjoining class is interfering. But that works. So you need to be on channel 41 for it to work. And those of you using ResponseWare with your mobile device, there's the session ID number for this time. So you'll log in through your app or through a browser. And when it prompts you for the session ID, there you go. And I always give you a little more time on the first one so you can do that. And again, yes? Yeah, in ResponseWare you can enter that, right. It shouldn't matter. I'm leaning slightly towards the name just to eliminate confusion and that one less step for me of looking you up. It shouldn't matter even if it's blank, because if you registered through modules, made your account, your ResponseWare device ID number is associated with you and it should go to your name anyway. But in case that messes up, it's nice to see who you are. Then I can come talk to you and say, hey, there seems to be a glitch. So that in that case, a name might be useful. Okay, so this is how I typically use the clickers. I have a question here. I open polling like this. You ought to see now that you can respond. And this is out of chapter 3 stuff. Sophia's running along the aisle of a train car that's moving at 8 meters per second. So you know how fast the train's going. Sophia's speed relative to the floor is 3 meters per second. So in her frame of reference on the train, she's moving 3 meters per second. Her speed relative to observer at rest on the ground, watching her and the train go by, what would that be? And if you've never done this before, you choose an option, say you choose A. You should see a check mark or something indicating it worked. And if you change your mind, just click another answer. As long as my poll is still open, you can change your answer as much as you want. Yes? Can't open. You can't send a message, but you can answer the... Yeah, send message is not open. So we'll say, oh, yeah, you're... How do we go back? There it is. Let's go back. You're trying to send a message instead of answer the question. So say you think it's A. Just enter A. Check. Now enter what you really think it is. So in case others are having the issue, she was trying to send a message instead of just hit the answer, which these new fancy clickers have the option to do. So let's see. We can see we have 33 responses. There's more than 33 of you, so... Her speed relative to an observer at rest on the ground. So yeah, stand not on the train. And let's see yours.
It says I go into channel 41.
It says you're on 41 too.
Yeah, but I can't do anything.
All right, let's go back. See the little arrow? All right, now say you just do A.
No, I don't want it.
What? You can change it. I'm just. It's like I just said. It's not the final answer until I close the poll. Anybody else having issues? Well, hey, that's good. That's the least amount of issues the first time ever. All right, 40 of you. So I close the poll, and it shows responses if you're curious. Yeah. So most of you think D next, and then you're kind of split. So I have the option to let you guys discuss it, which sometimes we'll do, and answer again before I give you the right answer. But this time I won't. I'll just tell you that the correct answer is D. This is a vector thing. There's more than one vector happening. So they're either going to add together or subtract together. So you guys are at rest on the ground, and the train's moving along at 8 meters per second. If I'm the train. Now pretend like I'm Sophia on the train. The train's going that fast, but I'm going 3 meters per second relative to the train. Sophia runs along the aisle of a train car. So she's inside. Well, and this is a good example. If this ever happens on test day or even homework, you ask me. This will sound bad, but you'll know what I mean. I'd rather you miss it because of getting the physics wrong than not understanding, misinterpreting it. So always ask me if there's something like that. I apologize. Yeah?
Do you put these on WebAssign after the day?
This one, no. But they're video recorded, so you'll have them.
Oh, okay.
And we usually spend enough time on them that you can jot them down even if you wanted, or snap a picture. I'm not offended. But yeah, I grab all the questions too. It's another option. I have a pool. There's the questions in the book. There's questions from the author on WebAssign. There's those. I ask questions on homework, these pre-lecture questions, clicker questions, and test questions. They're all the same format. They're all from the same pool. Sometimes I make them up, but I follow the exact same format. So the type of questions you're seeing now and you've been seeing on homework and you see in the pre-lectures, there won't be surprises come test time. When I go through them, I essentially just go, oh yeah, I like that one, homework. I like that one, homework. Ooh. Now let's put that one on the test. So there won't be any surprises. So back to this one. I guess it probably makes more sense now why it's D to more of you, since we had a bunch of, oh. So if the train's moving 8 that way, and she's moving 3 on the train, then they would add. It's like a big vector 8 and a little vector 3, and they'll add on top of each other. It could be 11. How could it be 5? If the train's going that way and she's walking this way, then they would subtract relative to you at rest watching, because the train's going one way, she's going the other, so it'd be like this. And it's the net vector. Does that make sense?
So if you were to put it on a graph and you were watching and she was running the opposite direction of the car, would it technically be like a negative or an opposite direction, like a -5, because the car is subtracting?
I see what you mean. Yeah, wouldn't it be a negative the other way? Bottom line, relative to you watching her go by, train goes that way, she's walking this way. Which way relative to you will she ultimately be moving? What's your gut say? Yeah, the train's moving that way, but she's moving that way. So
With the train moving at a faster speed,
the train is going faster, so she's going to end up going that way, which is why it doesn't end up being negative.
yeah, okay.
Let's draw it. I always say, I like pictures, right? So if the train is 8 and that length represents the magnitude, then 3 that way. And so they'd add to 11. I think you can see that. If it was 8 and 3 that way, it's like you can take this much off of this one, and you're left with a net of 5, but still that way.
Yeah, I guess I was just imagining it like relative to an axis where like you were 0, and then we could either move here right or left. So
Yeah. And we could mix everything up and say the train's going the other way. And now, is it negative now? Well, if we said this way was positive originally, then yes, and this is now negative, or vice versa. They're opposite. Let's try another one. All right, polls open. You should be able to respond when you're ready. And as you're thinking, I could ask these questions normally in class and lecture without clickers, but as you've already seen, most students don't respond. And of the half probably that aren't responding, they really aren't, they're not responding at all, they're just sitting there. The main reason I use clickers like this is to get you to commit to an answer, or when I ask you a prediction or something later in the semester. Because you learn more when you actually commit, whether you're right or not. Once you learn the correct answer, it'll mean more and stick with you more than if you just sit there waiting for the answer. Second, it helps you guys, I think, kind of gauge. We've been discussing some of this stuff. See how you're doing, because this is what type of stuff I'll ask you on the test and the homeworks. Let's see, 39, there's one more of you, so I like doing, that's most of you. I just count down, and those of you that have been waiting can get it in. 10, 9, 8, 7, 6, 5, 4, 3. I see we gained 2 more people than last time. 3, 2, 1. All right, most of you C, and next A. The correct answer is C. Okay, somebody that chose C, would you be willing to share your thought process? Yes.
So the ball is increasing in speed each second by the same amount. Its acceleration is it's accelerating the same speed each second. So its acceleration is constant. Is that kind of funky?
All right. Anybody want to? Oh yes, go ahead.
If you're imagining it as like a graph where you do it like time over distance and then you measure the rise and run, and you know it's the same, then the slope of it's going to be the same the whole time. So calculate the acceleration, you're going to get the same number.
Okay. I'll repeat some of these in a moment. Does anybody still want to defend A? I mean, it's okay. Does it make sense now? So yeah, you can look at a graph like we graphed, and if it's changing the same amount as he said every second, it's like that slope. It's going to make a straight line. And so that slope, that change is constant. The change isn't changing also. You know what I mean? It's not like blah, 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 blah. So it's like free fall. Or no, let's use this example. It's going to change 4 meters per second every second. So the acceleration is constant. It's 4 meters per second squared. You good? Okay. 26. Polling open now. So how about a falling raindrop? If your first thought is, I don't know, he didn't give me any numbers. That's why it's a conceptual physics class. Think about what's going on. You don't need any numbers for this one. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. I know there's 2 more of you. Come on, 1 more. Going once, going twice. Large majority of A saying it's 0. You're correct. The idea here is if the velocity is not changing, what's acceleration? It's the change in velocity with time. It's not changing, so the acceleration has to be 0. Now, I'll predict. Those of you that got stymied by this one is like, but it was falling. It was accelerating down. Well, what must be going on if it's no longer accelerating but still falling? Somebody read the book, Terminal Velocity, and what did you say? It's falling at a constant rate of acceleration? Yeah, because we just said acceleration 0. So it's no longer accelerating. It's not falling any. It's not getting faster and faster. It's not slowing down. Yeah, it's constantly staying put. But the Earth's pulling on it, trying to accelerate it. We know that hasn't disappeared. Yeah, the 9.8 meters per second squared is the acceleration due to gravity trying to accelerate it and speed it up downward. But it's not speeding up. So something is retarding it. There must be a net force of 0. Otherwise, it'd be accelerating. And yeah, that's air resistance, which we'll get to. It's terminal velocity. That's what it's defined as. You can fall faster and faster and faster, but at some point, if you stop increasing how fast you fall, you just stay at that velocity. That's why it's called a terminal velocity. It's a constant velocity. You just don't go any faster because now air resistance is keeping you from going any faster. So you have 2 forces balanced. Weight pulling you down and air resistance holding you back. 1 more I chose. Just got to remember what it was. Slide 36. All right, go. And given our very last clicker question, remind you that free fall is only under the influence of gravity. So you can ignore air resistance. Since there's only half of you, I'll give you another clue. It's actually conceptually just like our example we worked. But instead of going horizontally, it's vertically. We started at a certain position with a certain velocity, and we started accelerating under the influence of gravity. It's just going this way now instead of this way. All right, talk to your neighbors. There's several of you that are still aren't sure. Go ahead, talk to your neighbors. See if it helps them out or changes your answer. Choose somebody near you. Tell them why what you're thinking. Those of you that are like, I don't like this, I'm not playing. Well then, I won't force you, but you'll find this useful. What I really want to make you do is find someone that doesn't agree with you and talk to them. One thing I hope this teaches you is that you guys can use each other as a resource. I've been doing physics for a long time, and sometimes I try really hard to remember how I thought, but you know, I won't lie, this comes easier for me now than it does you. So the way you guys are thinking and approaching it is useful to each other. All right, let's see. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Okay, most of you, 2/3 of the class, think it's C, and you are correct. Now I'm curious, how many changed their answer to C after talking? Well, good, it influenced at least one person. How many changed their answer away from C? Oh, there was one of those too. All right. Okay, so what's the acceleration rate? 10. 10 meters per second every second. So in exactly 1 second later, it'll change by how much? 10. What did it start at? So what will it be at? 40. Started at 30, it will be at 40 exactly, which is the only answer is more than 35.
35 would have been like the average between the two.
Very good. 35 would have been the average velocity for that second of fall, because it started at 30 initially, instantaneous. The final instantaneous is 40. So on average through that second, yeah, you can say it was going 35 meters per second. Very good. Questions about that one? Okay, you can put your clickers away. I want to remind you that when you attempt to log into WebAssign, continue my trial period. There's 2 days remaining that you would see. Oh, you know, while you guys are putting those away, I'll actually close the session before I forget. All right, back to... So friendly reminder that you will need to choose this option, Purchase Access Online, to continue doing your homework and getting credit after 2 days. So those of you that haven't, most of you have, I've seen, but some of you haven't, that's what you'll need to do to continue. I'm going to continue. Get in there and show you that over here in announcements, there's where the videos are posted. Here's how the grades are. Our TA information. I posted that right here. I told you he was Muhammad, but he has chosen office hours and time. And we chose 2 different, in case some of you couldn't make one of them. And they're there. And it's kind of small, isn't it? There, that helps. So Mondays and Wednesdays at 2, and then Friday at 4. He'll be there working on his homework. But he is very willing, he's extremely nice, to help you. I strongly encourage you to use him as a resource if you're not getting any of this. Me too. You can contact me, you can meet with me, we'll arrange, we'll find a time that works. So you have him and me and each other. But he's going to do that every week. There's a fixed time. So that's where he's at. If you don't know, this is the James Fletcher building. 209, it's over there, not the round portion, up on the 2nd floor. He's in there with other graduate students, so he has a desk number. Okay. Any questions about WebAssign or how that clicker stuff went just now? Okay. Great. The pre-lecture questions. Oh, I meant to leave that open. I'm going to do that. We don't need to display this video guy. I'm just opening this up to view them, to remember what they were. So you don't need to show this to the class. The first question was, the force of friction between two surfaces can act, and then it prompted. And see, that reminds me, this was the next thing I wanted to do. So here's friction. We've discussed it already. You kind of already know what it is. It's a force, and it opposes motion, or as I love how the book puts it, intended motion. How's I word that? No wonder, wrong page. Okay. Force that acts to resist the relative motion or attempted motion of objects or materials that are in contact. And that's straight out of the book. So to show you what I mean, demos. So here's a block. I'm going to make it even heavier just so it's more emphasis. And the idea is, this is a spring scale. If I pull on it, I'm applying force, and it shows you how much force. So see, I'm applying force, but it's not moving. So let's draw that. I don't need these. I'm pulling. What's the net force on the block? Is it moving? So it's 0. Well, then what's that tell you? There must be a second force, and I bet you know what it is. Friction. And in that case, it's the same in magnitude, but opposite in direction. So F pull one way minus F friction the other way is equaling 0. That's summing, oh, that was pretty. Summing our forces means the net force is 0. So friction acts even if the thing's not moving. We're attempting to move it, and the little molecular structures in between there are resisting. We call that, by the way, static friction. That's when it's not moving. Hence static. So let's see. I'll pull on this slowly. Let's see what we get up to. Oh, there we go. And now I move it. Look what's some observations, you good scientists. We got up to about 13 before it started moving. That time it got up to about 11 before it started moving, but then what happens? It needs less to stay moving. So if I were to pull this at a constant force, which is hard because this isn't uniform, the idea is it gets moving, but then it breaks free, and then I try to hold it at a constant force, which I'm not too good at. But you can see that it's less than how much it took to move it in the first place. Did you see that okay? Well, let's do that case. Now it's moving. The velocity is not 0. I'm still pulling it. There's still friction. But how should I draw this length? Shorter will be obvious. Friction. So the net force is not 0. Yes? Correct? Which means, what about the acceleration? It's not 0 either. Can't be. It's changing its velocity. If I can pull with a constant force. But let's think about this. Does it look like it's accelerating? Here, just so I have more room, let's do it on here. I try to hold it at 6 there on average. Does it look like it's going faster and faster? No. You know, it's always good to use your gut. Galileo, do an experiment and see, wait, this isn't accelerating. All right. That means the acceleration is 0 when I'm maintaining an equal force. That means the net force must be 0 as well. What's that mean about this then? Should be the same length. Now those of you that are annoyed because, dang it, I already drew all this, you'll remember it better now. Those must be the same. But how do the magnitudes of these compare to the magnitudes of these? We'll do it again. It's not moving. Top case. I can get up to 11. Oh, they're 11. But to keep it, maybe 9 or 10. So you are correct. The magnitude here, I should make sure those are bigger than down here for emphasis, right? This is a kinetic friction, is its name. Kinetic meaning it's in motion. And your book defines these also for reference. So the idea here is these are both equal but opposite, and these are equal and opposite. It's not accelerating. What would I have to do to get it to accelerate? In either case. Pull it harder. You saw it. We can say, if this has a certain static friction, then for me to get it to move at all, I have to exceed that initially to get it to change its motion and go from 0 meters per second to something meters per second, thus have an acceleration. But then, as you saw, I tried to move it with a constant force. And I'm much better at that on the table. For it to accelerate, I'd have to pull a little harder at first. You see it jerk. My point here that I'd love to emphasize is that, again, you can be moving and not accelerating. You're like, yeah, that one makes sense. But it also means you have forces acting on you, but they can be in balance. It's just, again, like your car going 80 miles an hour. You're exerting a force trying to propel yourself forward, but there's resistance and air resistance trying to hold you back, right? And if they're balanced, you don't change your velocity. So the force trying to move in the first place, again, is static. Once you're moving, it's kinetic. They're not the same. And this one is always greater than or equal to friction, depending on the situation and materials. And you can see that this has more friction than the table. I don't even need to use this piece of Teflon, which is even slipperier. Here's a fun way to do it. I took a movie, some of you might have seen this, and I just interwove pages of a phone book together. It didn't come out very pretty, so I watched a second movie and redid it. But they're just this every other page. I just laid them on top of each other. No glue, no tape, nothing. I did put tape on the outside only cover, a little piece of Scotch tape, just so it doesn't unravel. Now we can play tug of war. I need 2 volunteers. I want to see if you can overcome the friction. Mark's 1, great. Come on, sold, come on down. So I just use these pieces of wood to sandwich because it's really hard to grab a hold of. And your job is to try to pull these books apart. Go. Harder. Come on. Come on, Mark, you're strong.
Yeah,
Pull him. All right, this proves my point. Give him a hand. Thank you. I actually mounted this one day, these ropes and pulleys, and I hung from it. So the point is, there's a whole lot of friction there. Friction can create a lot of force. But the reason this one's so strong is a support force. Something called a normal force, which we've discussed. They're pushing against each other, right? They're just like on an incline. This incline supports it, even at an angle. Well, the pages are pushed against each other. And you know what? The heavier this is, the greater the normal force. So when you pull this apart, you're actually kind of squeezing it together as you're trying to pull it apart. The formula, the equation that guides our thinking is this symbol mu represents a coefficient of friction. Coefficient of friction. And that's different for static versus kinetic. For different materials, you'd look it up in a table. It's a constant for those materials. Times the normal force. This would be the frictional force. That's the relationship. We won't need to be putting numbers into it. We just want to know that if you increase the friction, the materials, it's going to take more force. Table versus cork and sandpaper. But also, the more they push on each other, you can increase the amount of friction. So much that you guys can't even pull it apart. You can go home and try it with a deck of cards. If you shuffle them, put them together. If you grab them from the sides like this, piece of cake. But if you do it again, a lot like how the telephone book's set up, if you squeeze it here and try to pull, as I pull, the cards are trying to push against each other. That increases the support normal force and thus the amount of friction. And it's really hard. If you think I'm fooling you, you go home and try it. How many have tried these Chinese finger cuffs? And I realize it's ironic because they don't have these in China. Or they're not from China. But, and then you're like, I can't get out. And then the harder you try to pull, the more they squeeze down on you. Increase that normal force. Increases the amount of friction. And you have to pull even harder to do it. So, you learn as a kid or now with physics, wait a minute, let's lessen the normal force. All right? Kind of squish them together. Piece of cake. So that's fun. All right, with the last bit. See, I intend to use these pre-lecture questions to help us teach stuff. The second one was, when we say that 1 kilogram weighs 10 newtons, what do we mean? 1 kilogram is 10 newtons. So the mass is 1 kilogram. The weight is 10 newtons. What's our relationship between those? That's our relationship. This is where we're going to cover more next lecture. You've seen this before. We're going to start understanding it more. but you did weight. What is this mass of 1 kilogram being accelerated at downward? Yeah, it's the acceleration due to gravity, and that's 10. That's why we say something with 1 kilogram times 10 meters per second squared is 10 newtons. But that's only true on Earth. If we went to Jupiter where this value is different, it'd be accelerating at a different rate, and it would weigh something different. So something to realize is weight can change. Those of you that weigh yourself every morning know that. But I mean, thank you. But mass doesn't. If you're 1 kilogram on Earth, you'll still be 1 kilogram on the moon. But you'll weigh different because you're being accelerated at a different rate. Does that make sense? All right, to end, I want to make you aware and remind you that on WebAssign, past homework, you can go back and view those and click on the answer key. Once you do, you're committed. You know, I can see that you've seen the solutions. But I put explanations to many of those, little 1 or 2 sentences. So if any of those gave you problems, or definitely before the exam, go back and look at those to make sure you're understanding what I was hoping you understood from it. Because if my explanation still doesn't make sense to you, but those are there for you, so included with these pre-lecture questions. I have already, well, in a minute, you ought to be able to see, I already entered it, Monday's pre-lecture questions. More on Newton's second law. What's that? Correct. Right before this class was the first time, as I warned you and reminded you Wednesday. So from now on, we'll have those to preempt you to think about this stuff. So when we discuss it, hopefully you'll remember it better by test time. Any other questions? Have a great weekend, folks.